Okay, so we're going to look now at the second method of preparing alkenes, which is from preparing alkenes, which is from alkynes. So again, just to put things in context, we had explored the fact that preparing alkenes would either happen from eliminating HX from saturated. And really, to be more accurate, I can actually make this, let's make this AB, right? Because it turns out, this could either be HCl or HBr or HOH or BRBr, right? So it's from AB species to generate the alkene, or we can philosophically prepare the alkene by partial hydrogenation of the alkyne. So we explored three methods of the elimination. One was dehydrohalogenation, and all of the baggage that came with that, E1, E2, and partitioning SN1, SN2 stuff. CHS rule and all kind of good stuff. One was dehydration, and that's very involved because that is the first time we've seen carbocations undergo rearrangements. And that rearrangement is not unique to dehydration. It happens even when we're doing reactions that involve SN1 reactions. So for example, just to give you an example of that, if I were to take a compound of this nature, and let's say this is an iodide, and we have this in, let's say, a solvent like methanol. So this is a really good leaving group. This is a polar ionizing solvent. So what would happen is we would lose iodide, give rise to the carbocation. That carbocation, it's secondary, it can rearrange, and when it does, it'll give rise to the tertiary carbocation. Right? I'll do a methyl shift, make the tertiary carbocation, and then that will be attacked by methanol to give rise to the corresponding ether. Right? So technically what we get first is the oxonium ion, and then another methanol would act as a base, pluck off the proton, and give rise to your product. So what you end up with is the corresponding ether. But the point is that you would not simply get the O-Me at that position. Because under these conditions, which are SN1 conditions, you make the carbocation. If it can rearrange, it will. And again, the rearrangement is intramolecular. It's going to happen very rapidly, a lot faster than a methanol attacking the species to make product. So if you were asked what are the products of the reaction, the major product would be this. Right? The major product will be this. There will also be some where that species gets attacked before rearrangement, in which case you will get the plus and minus products, because attacking this site would give you a stereocenter here. Right? So technically, there will be three products of this reaction. The enantiomeric pair of the secondary ether, and then the tertiary ether, which is just the one. But I mentioned this just to say that rearrangements are not unique to dehydration of alcohols. Once you make carbocations, rearrangements are possibilities, and you want to be aware of those. Which is why we say, if you have a choice, synthetically, you want to try to avoid carbocation formation. Okay, so we've explored the preparation of the alkenes by elimination. What we want to do now is to prepare alkenes from alkynes. So our second big topic, 2, is from alkynes. And we're going to subdivide this into 2 types. One is, let's go to A, is partial hydrogenation. And then B would be from lower alkynes. So let's do the first one. If I treat, let's say I start off with 2-butyne. If I treat 2-butyne with, let's say, excess hydrogen gas and platinum in ethanol at 25 degrees Celsius, those are the classic hydrogenation conditions, I'm going to generate butane, right? Technically, I can either say excess hydrogen gas, or I can simply say 2 equivalents of hydrogen gas. Right? One equivalent will saturate one pi bond, the second equivalent saturates the second pi bond. If I use these conditions, because platinum is actually pretty impressive catalyst, that will drive the reaction to completion, and that's complete hydrogenation. But it is possible to do a partial hydrogenation of the alkyne, right? I'm going to say partial hydrogenation, and only quench one of the double bonds, one of the pi bonds. But if I take butane, 2-butane as my substrate, and I quench only one of the pi bonds, well, that means one of them remains, and I can either get the cis alkene or the trans alkene. So the immediate question to ask is, well, and as an organic chemist, fine. If I can get both, can I configure my conditions to get either exclusively one or the other? Because of course, this is a very powerful tool to be able to make at will either the trans alkene or the cis alkene. And the answer is, we're organic chemists, we can do anything, right? So I can actually then get the cis alkene if I use the following. So I'm going to treat this with hydrogen gas and Lindlar's catalyst. Or I can use hydrogen gas and what's called a P2 catalyst. If I wanted to do the other reaction to make the trans alkene, I would use sodium or lithium in ammonia, this is liquid ammonia, or a liquid primary amine. And we'll talk about these in some more detail. So the bottom line is, I can either do complete hydrogenation of an alkyne, which gets me the corresponding alkene. And there are times when I want to do that, then that's fine. But what's much more sort of interesting is that I can partially hydrogenate an alkyne, and in the process generate either the cis alkene or the trans alkene, and I can do this at will. Let's look at the first example. Look at details of the first example. So how do we do the partial hydrogenation, and how do we get the cis alkene? Well, Lindlar's catalyst is basically a palladium catalyst that's poisoned. So it's normally poisoned with something called quinoline, quinoline is a typical poison that they use, although sometimes they use calcium carbonate. Right? So Lindlar's catalyst is a poison version of a palladium catalyst. Now palladium and platinum are actually really good catalysts for hydrogenation reactions. But if you add quinoline or a couple other reagents you can add, what you sabotage the palladium's ability to drive the reaction all the way to product. So you can simply go from the alkyne, the 2 pi bonds, to the alkene with 1. Okay? The P2 catalyst is a nickel boride catalyst, and we won't talk about that in much detail. But what is interesting is that, regardless of which catalyst you use, the way this reaction goes is that you add hydrogen gas to the system. The hydrogen gas gets absorbed onto the catalyst surface. So the hydrogen gas gets absorbed, right? And then the alkyne comes along and sits down. So eventually what's going to happen is that these 2 H's get added from the same face of the alkyne, and that gives rise to the cis product. And we've seen this cartoon before when we looked at hydrogenation of alkenes to make alkanes. So the hydrogen gas adsorbs, this is ADSORB, right? So it's adsorption is a surface phenomenon, right? It's not a bulk one like absorption. So like a sponge absorbs water. That's absorbs with a B. So the water is actually in the entire body of the sponge. Adsorption is a surface phenomenon. So you might have an oil slick on the surface of water, or on the surface of your driveway. Well, that's an adsorption. It's just on the surface, right? So the hydrogen gas absorbs onto the catalyst surface, and basically what it does is I use these two electrons, the sigma electrons in the HH bond. They bind to low-lying orbitals in the catalyst, but I'm using now two electrons to zip together 1, 2, 3, 4 particles, and that makes the HH bond very weak. And so now I have a weak HH bond, a weak pi bond, so this reaction goes very, very nicely. But because of the geometry of the chemistry of the reaction, because the H's are sticking up this way, when the alkyne comes and sits down, it plucks the H's on the same face. So you end up with the cis alkene. So if I treat the alkyne with hydrogen gas, either with limitless catalyst or the P2 catalyst, that's going to generate the corresponding the cis alkene. The other reaction is a bit more exotic. If I use sodium either in liquid ammonia or liquid primary amine. Now, this is not aqueous ammonia. This is not what people mislabel as ammonium hydroxide, right? This is ammonia gas condensed. This is minus 120 something, I think, degrees Celsius. No, it's not quite that low. Minus 80, I think. So what you get is liquid ammonia. If you dissolve electropositive metals like sodium and lithium in liquid ammonia, the most peculiar thing happens. And the best way I can think of it is what happens when I take sodium chloride and put that in water. And the answer is it splits up into sodium cations, which are solvated by water molecules, and chloride ions, which are solvated by water molecules. So basically water molecules surround them in a sphere. If I take sodium metal, so there's a lone electron on the sodium, right, the valence electron, and I put that in liquid ammonia, it breaks up into sodium plus, which is solvated by ammonia, and an electron, which is solvated by ammonia. So in a sense, it's sort of a parallel phenomenon. The sodium dissociates into the cation, which is surrounded by ammonia molecules, right, the N side pointing in, and the electron, which is surrounded by ammonia molecules. But in a sense, that electron is a free electron, and that makes that system very interesting. On the one hand, it has metallic properties. So sodium is dissolved, when dissolved in liquid ammonia, gives rise to a silvery blue solution. It is one of the prettiest things I've ever seen. It looks like blue mercury. It's really quite beautiful. But the sort of silvery feel to it is because it's got a free electron, and you'd meet this in physics or in PChem. But from a chemical perspective, having free electrons gives you the potential to be a very potent reducing agent, right? Because reduction is a gain of electrons. These electrons are swimming through the solution, you know, solvated by the ammonia molecules, but they're available to carry out chemistry. So the way this happens is if I treat the alkyne with sodium in liquid ammonia, what happens is the following. The sodium donates a single electron to the alkyne, and what you get is this species. We end up with, I'll draw it this way. And we lose Na plus. Now, what I want us to do is some bookkeeping. So I'm going to focus our attention only on the 6 electrons in a triple bond, 2 in each bond, 2, 4, 6, and the 1 electron on the sodium. So at the start, I have 6 and 1, 7 electrons. I have 2, 4, 6, and 1, 7 electrons. So this carbon, this vinylic carbon, now has a negative charge, because the carbon has 1, 2, 3, 4, 5 electrons that belong to it. So it's a negative charge. This carbon doesn't have a negative charge. It's got 4 electrons, 1, 2, 3, 4. But it's both a radical, because it's a lone electron, and an anion, because I've got an electron pair and a negative charge. So this species is called a radical anion. Organic chemists are not imaginative when it comes to naming things. But we've made that radical anion in the presence of ammonia. And ammonia is a protic solvent. So it's a no-brainer what happens next. If you make C- in a medium containing a protic solvent, it's a no-brainer that what happens is the ammonia donates a proton to the radical anion, and we end up with this species, which is now just a radical. And there's a point I need to make here, but I'll come back in a second. Well, the radical is still in the medium which contains sodiums. So the sodium will donate an electron to the radical, and that's going to generate now the corresponding anion. The anion, again, is in a medium containing protons, containing ammonia molecules, which act as proton sources. And so what we'll end up getting then is protonation, and we make our corresponding trans alkene. There are 3 points I think that need to be made in this scenario. One is that the electropositive metal, like we use with sodium or lithium, they work really well. Notice the initial arrows. It's a fish hook, meaning that the sodium donates 1 electron, and a full-headed arrow. So 1 electron comes in here, and these 2 electrons in the pi bond get deposited onto that vanillic carbon. So this is the first time we've seen a 1 electron and a 2 electron shift in the same mechanism, the same step. That gives the anion gets protonated to make the radical, which gets another electron to make the anion, which gets protonated. The other important issue here is that when the alkyne got the initial proton, the geometry of the product was set. Because I could have drawn this as if it was going to make the cis arrangement. But the alkyne is linear. And if it has the choice, when you get the electron in, it has the choice, it now has to go to being trigonal planar. It has the choice of setting up the 2 alkyl groups cis or trans. And because the trans is more stable than the cis, it invariably adopts the trans geometry to make the more stable intermediate. So really, the stereochemistry was set up in step 1. The third point I'll make is that if you notice this reaction, the C- deprotonates the ammonia to make NH2-. NH2- is a very strong base, and normally you do not lose strong bases. The problem is this is not quite right, because the NH2- is formed in a medium containing ammonia molecules. So really, this ammonia, this N, was hydrogen bonded to an ammonia molecule. And this is also hydrogen bonded to another ammonia molecule, and so on and so on and so on. So when I dump these electrons onto that N, they don't really belong to that N. Right? I've drawn it on a single N for bookkeeping purposes. But in reality, that negative charge, as I dump it here, I could have formed this NH bond to give ammonia, and therefore I can pull off this H and make the NH2- here, pull off this H and make the NH2- here. So basically, that minus charge is disseminated through the medium, right, via hydrogen bonding. So it's not as if I'm making a single NH2- species. I have 1,000 N's all sharing the 1 minus charge. So it's not as bad as it looks. I just do this for the sake of bookkeeping. Okay, so we can prepare alkynes, we can prepare alkenes, we can prepare cis alkenes from alkynes, from internal alkynes, right? Meaning that I've got, the triple bond is internal, right? They've got R's on both sides. I can make the cis alkenes using hydrogen gas and Lindblers catalyst, or hydrogen gas and a P2 catalyst. And I can make the trans alkene using sodium or lithium in liquid ammonia or a liquid amine. And we've gone through the mechanisms for both. A true mechanism for the latter, and sort of a cartoonish mechanism for the first one. The other way of making alkenes from alkynes is from what we call lower alkynes. and I'll qualify that in a second. A lower alkyne is simply an alkyne with a smaller number of carbons. And really, what we should say is from lower terminal alkynes. From lower terminal alkynes. And just to remind ourselves what this means, if an alkyne has an H on the end, that's a terminal alkyne. If the alkyne has alkyl groups on both sides, whether they're the same or not, then this is an internal alkyne. Right? This is terminal. So how do we make higher alkynes, for example this one, from lower alkynes? That's the question. Well, here's how we do that. We take advantage of the fact that terminal alkynes are modestly acidic. And they're acidic because the carbon that's attached to the H is sp hybridized, which means it's modestly electronegative. And also, it stabilizes the negative charge once you've pulled off a proton. There are two bases that are typically used to deprotonate a terminal alkyne. I can either use NH2 minus, so amide, which normally comes as sodium amide. So it's called sodium amide or sodamide. Or I could use something like butyl lithium. That's another typical example that's used. So N-butyl lithium. They will generate the corresponding acetylide. If I use NH2 minus, I'll get ammonia. If I use butyl lithium, I'll get butane coming off. The acetylide is a nucleophile. And so that actually can react with other haloalkanes, let's say R prime X. I can do an SN2 reaction, and that's going to generate the corresponding internal alkyne. And then from here, we can go and do our either sodium in liquid ammonia, or we could do a hydrogen gas and a lipless catalyst. And that's going to give me R, or corresponding cis species. Okay, so that's the preparation of alkenes. The last thing we do is reaction of alkenes, and we're going to limit it just to a few, where are we now? We're going to limit this to just a few examples. So I'm going to go ahead and erase this. So, reactions of alkenes. Alkenes are interesting species in that, as we mentioned in class, these carbons are sp2 hybridized, and the species is trigonal planar. But the pi pair confers on an alkene both a nucleophilic and basic character. In addition, because, that's funny I said that, but the carbon-carbon double bond promotes addition reactions because the pi bond is weak, and what this system would want to do is react with AB to generate A, B, right? So basically, I'm going to replace a pi bond and a sigma bond by two sigma bonds. So alkenes tend to undergo addition reactions fairly readily. Because they're nucleophiles, then the species that attacks them, the AB species, will have to be an electrophile. So typically what we see with alkenes is electrophilic addition. Okay, so let's see what are some of the reactions of alkenes. Well, the first one, which we met a long time ago, is hydrogenation. Right? I'm not going to spend much time on that except to say that alkenes will react with hydrogen gas and platinum. We just talked about it with the alkynes a second ago. 25 degrees Celsius with ethanol and generate the corresponding alkane. And that's the whole concept of the, the alkene being flat and coming to sit down on two H's from the catalyst surface, and they come from the same side and you get product. That's kind of important because if I take, let's say I have this compound, and I treat this, I treat that with say D2 and platinum in ethanol at 25 degrees Celsius, what my product will be is that where the two D's are going to add from the same side, and that creates stereochemistry in the molecule. And I can have this species be methyl. Okay? And these two species are enantiomers of each other, right? They're mirror images of each other. So there's a consequence to the syn addition that happens in hydrogenation reactions. And obviously I can either add D2 or T2 or whatever, or whatever. So that's hydrogenation. The other reaction of alkenes is, is hydrohalogenation. And if you recall, when we were classifying reactions, you said that ation means addition of, and the thing that precedes ation is what you're adding. So hydrogenation is the addition of H2. Hydrohalogenation is the addition of a hydrogen halide. So let's take an example. Let's say I had propene, and I want to add to propene HCl. Well, the thing that immediately sort of pops up is that the alkene, this alkene is unsymmetrical. Right? I've got a methyl on one side, no methyl on the other. So technically, there are two ways I can add the HCl, right? I can either add the H here and the Cl here, right? Which would give rise to this product, right? Where the H went here and the Cl went here. Or I could do the alternative, where the H goes here and the Cl goes there. And that's going to give rise to the alternative product, which is this one. Right, where the H goes here and the Cl goes here. So that's a question then of regiochemistry. Right? What is the regiochemistry of the reaction? Which one do I get? Can I control the reaction to get one or the other? And if I'm going to get both, can I make a preponderance of one or the other? Well, it turns out, if you carry out this reaction of the alkene with HCl, of this alkene with HCl, you see none of this. The only product you get is this one. You see none of the primary halide. So that's an interesting question. How the heck did that happen? In order for us to account for how it happened, what we want to do is to see why it happened. In other words, to look at the mechanism of the reaction. Well, this is fairly straightforward because we've seen lots of familiar triggers. HCl is an acid. Acids do one thing and one thing only, seriously. They do one thing and one thing only, which is they protonate. Who do they protonate? Bases. What makes me a base? Having a lone pair or a pi pair. So the HCl is going to react with the acid, and herein lies the issue. The H could either go on carbon 1, but if it does, there'll be a positive charge generated on this side. Loose chloride. So either the H goes on carbon 1, in which case I make a secondary carbocation. The alternative is the H goes on carbon 2, but if it does, I'll make a primary carbocation. And that is simply not an option. Because primary carbocations are too unstable to be formed, so we don't see any of the primary carbocation. Right? That does not happen. So the only carbocation that's generated is the secondary one. So when the chloride lost in that step is looking for a soft place to land, it just sees the secondary side. So the chloride attacks, and we generate our 2-chloro product. Now there's a term we have to get familiar with. When a reaction has the possibility of giving 2 different isomers, where the regiochemistry is either H here and Cl there, or H here and Cl there, so the regiochemistry is different. If I had 2 regiochemical options, and I only make one, this reaction is said to be regio-specific. So the reaction shows regiospecificity. Because of the 2 potential options, I only make one. This is a different scenario from this case. If I had this alkene, and I treat that with HCl, well, what actually happens is I end up with 2 products. I end up with this one, which is the tertiary halide, and I end up with this one, which is a secondary halide. Now that's going to be a plus-minus mixture. How does that happen? Well, not surprisingly, the alkene can act as a base, it attacks the acid, and I can now make 2 carbocations. I can make the tertiary carbocation, and I can make the secondary carbocation. I'm going to make it simple first and then we develop a bit more. So when chloride, expelled in step 1, is looking for somebody to scavenge, it sees both tertiaries and secondaries, it'll scavenge them both and give rise to both of those products. Which is why I see both the products in the mixture. Well, really, I'm going to see all 3 products in the mixture. So let me amplify this a little bit. Let's diagram, in terms of energy, what's happening in the first case. So I have the alkene, I have HCl, and there is a certain energy level. The reaction is going to make carbocations. Therefore, it's going to be endothermic. So either I'm going to make the secondary carbocation, which is energetic, or I'm going to make the primary carbocation, which is going to be all the way up here. And I'm not going to write it on the wall. So in terms of relative energies, the secondary is stable, the primary is somewhere up here. And according to the Hammond-Leffler postulate, because the secondary carbocation is more stable, it goes via a more stable transition state. Because the primary carbocation is very unstable, it goes via an even more unstable transition state. So unstable, I can't reach it. Which is why I only get this product from this carbocation, I get regiospecificity. But in the case of the second reaction, that's not the choice I'm confronted with at all. So I'm going to have this alkene and HCl, and they're at a certain energy level, but they're generating either a secondary carbocation, well, let's make it a little bit higher. They're generating either a secondary carbocation or a tertiary carbocation. So both of these species are accessible, although the tertiary is accessible via a lower transition state than the secondary. So what's going to happen is I'll make more of the tertiaries than I will of the secondaries. And that in itself would suggest that the tertiary product would be the more abundant. Right? In other words, this is the major product, and this would be minor. But it's even worse than that, because many of the secondaries, once they form, will hydride shift to stabilize into the tertiaries. Right? I'll do a hydride shift. So right out of the gate, I get more tertiary than secondary. But some of the secondaries betray us and hydride shift into the tertiaries, raising the amount of tertiary, diminishing the amount of secondary. So the yield of the product from the secondary carbocation is smaller. You would note that because the secondary, this site is a pre-hydride is a pre-stereocenter. So I'm going to end up with both the plus-minus mixture, 50-50 of each. So the yield in this reaction might look something like 60% of this, 20% of the R, and 20% of the S. Right? And even that's a bit, I'm going to change that to maybe 70, 50, and 15. And even that might be generous. But let's stick with that. Okay. So that's hydrohalogenation. Now, let's go back and look at these reactions from a less rigorous fashion and see if there is a trend that is observed. So if I start with propene, I get this compound. This one is not observed. If I start with this alkene, right, I get this as my major product. This is major by far, and then I get these as my minor product. Is there a trend? The answer is yes. There is a rule called Markovnikov's rule. I think Markovnikov was Austrian, and like Zaitsev was Russian. There have been lots of changing of the spelling of the names. So sometimes you see two F's rather than a V. Markovnikov's rule applies to the addition of HX to an unsymmetrical alkene. And Markovnikov's rule is that in the addition of HX to an unsymmetrical alkene, the H goes preferentially to the carbon having the larger number of H's. So I'll say it again, Markovnikov's rule says that in the addition of HX to an unsymmetrical alkene, the H goes preferentially to the carbon having the larger number of H's. So what does that mean? For the first example, there are two H's here and one in this position. According to Markovnikov, the H would preferentially go to the carbon having 2, which means the Cl would go in that position. So I'm going to get the H here and the Cl there, and that's what I observe. In this one, Markovnikov says, look, there's one H in this position, there's none here, so the major product would stem from the H going here and the Cl going there, and that's exactly what we see. And it is interesting to note the reflection of Markovnikov's rule and Zaitsev's rule. Because Zaitsev's rule says when we're eliminating HX, the H is lost preferentially from the carbon having the smaller number of H's. So if we were going to take this compound and eliminate it, right? So this is Zaitsev territory using HCl. The major product, as you recall, would be this one. Right? That's my major product because it gives rise to a more stable alkene. So in the elimination of HX, we preferentially lose the H from the carbon having the smaller number of H's, 1 H versus 3. But when we're adding HX to an alkene, we add the H to the carbon having the larger number of H's. And it's important to remember Zaitsev's rule and Markovnikov's rules are observations. They don't explain crap. Right? They're not explanations. The explanations lie in the relative stabilities of the intermediates, of the carbocations you're generating, or the relative stability of the alkenes you're generating, and you're following the Hammond-Leffler postulate. So the explanation for Markovnikov and Zaitsev lie in the stabilities of your products of the step, alkene or carbocation, and the Hammond-Leffler postulate. Okay. That's hydrohalogenation. The last of the reactions, well, almost the last, is hydration. So hydration, this is 3, hydration. So I can take an alkene and I can hydrate it, which means the addition of water, in several ways. Now, there are several methods for hydrating alkenes. We talk about talk about one bad one, and then we look at the two better ones. So, if I treat an alkene with H3O+, there'll be an equilibrium that generates the corresponding alcohols. Let me just run through the mechanism here. The alkene will attack H3O+. That will generate, that's an equilibrium, it will generate the secondary carbocation, because I can't make the primary one. Then a water molecule would attack the carbocation, and that's going to give rise to the oxonium ion. And then the oxonium ion is attacked by another water molecule which functions as a base, and that's going to give rise to your product. And you get your reaction. If you notice here, two things are important. One, every step is an equilibrium. So your yield is never going to be quantitative, which is why it's not the best method. Two, the reaction really is acid catalyzed, because there's an H3O+ that sort of begins the reaction, that goes in, and an H3O+ that comes out. So H3O+ is a catalyst. So this is an acid catalyzed hydration. So point 1 is that everything is in equilibrium, every step is in equilibrium. Point 2 is that it's acid catalyzed. Point 3 is that the reaction makes a carbocation. And with that comes tons of baggage. The potential for rearrangement and blah, 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 blah. Well, and also, you'll notice this reaction is also a Markovnikov reaction, because the H will go to the carbon having the large number of H's, which it will do because that gives rise to the secondary carbocation. You don't make the primary one. So in hydration, I'm going to say A, the acid catalyzed hydration. Well, it turns out that we may want to do the reaction another way to give us a better yield. So I'm going to say B, so this hydroboration oxidation, and C, there is oxymercuration, demercuration. And let's do C first, which keeps it in context. So if I take the alkene and I treat it with mercuric acetate in water, followed by sodium borohydride, I'll give rise to the secondary alcohol in almost quantitative yield. How does that happen? Well, it's a little complicated in that mercuric acetate fractures in water, it ionizes in water, to give rise to HgOAc plus and OAc minus. OAc is acetate, right? OAc is just CH3, C-O-O minus. So this is the acyl group, or the acetyl group, AC. So ACO minus is that thing, okay? So This species, this is called a mercury-based cation, attacks the alkene. So I'm going to draw the alkene. And the mercury-based species, which is large, because mercury is a big atom, attacks, and what we generate is a rather interesting species called a mercury-bridged carbocation. You get a mercury-bridged carbocation. The mercury-bridged carbocation, so mercury-bridged carbocation. The mercury-bridged carbocation is a very interesting species, and there's something I've left out here, which is for a reason, which is, this is neutral, that's positive, where's the positive charge? Oops, I'm here. The species is interesting, because on the one hand, I have a mercury atom literally bridging the carbon-carbon double bond. But if you notice, for an unsymmetrical alkene, the mercury-bridged carbocation is also unsymmetrical. The mercury is not bang smack in the middle. It actually leans more to the side of the primary carbon. And why is that? For two reasons. One, because this whole thing is huge, it's going to shy away from the bulky side of the alkene, right? The side of the methyl group. So more of it is going to be on the right-hand side as I've drawn it, and so that's part of the reason, the steric reason for that. But the other reason is, in the mercury-bridged carbocation, the positive charge is delocalized over both carbons and the mercury. So I want to put more of the positive charge on the atoms that can better support it. Out of these two atoms, the secondary carbon can support more of the charge than the primary carbon. So the mercury has some charge, the primary carbon has some charge, but the secondary carbon has a larger amount of the charge. So what I'm going to do is I'm going to put more electron density in this carbon-mercury bond, right? Because this carbon is more adept at supporting the positive charge. So from both the steric perspective, hiding from the big group, and the electronic perspective, depositing more charge on the secondary carbon, the species is unsymmetrical. And what happens next is that water, because we're in water, right? Water attacks the carbon having the larger positive charge, and I end up with this species. Right, I end up with this species. Now technically I have OH2 plus, and then the water comes in and pulls the proton off. So what I've done then from here to here is I've added oxygen and mercury across the double bond. So that is therefore called an oxymercuration. Ation means addition of. What did I add to the double bond? Oxygen and mercury. So it's called an oxymercuration. In the last step, I'm going to treat this with something called sodium borohydride. I didn't write it down. So it's sodium borohydride. Boro is the element boron. Borohydride. And what that basically does is reduces the C metal bond to CH bond. So you end up getting this as your product. Right, without, well, let's do that. So what you've essentially done then is you've added the OH to carbon 2 and the H to carbon 1. Right, so you've overall then done an oxymercuration. This last step where we take off the mercury, that is the demercuration step. The one point I'll make here is that sodium borohydride allows me to introduce a single isotope of hydrogen. So instead of using sodium borohydride, I could have used sodium borodeuteride, in which case I would have gotten a D in this position, or of course sodium borotritiide, which will give me a T in that position. Okay? Now, this is really kind of remarkable now because it means, just to go back and give a big perspective, I can ask you to take this compound and convert it into this one. And put a T here. Well, that's going to be, and that is a Markovnikov reaction, right? So the oxymercuration, demercuration does Markovnikov. Let me just make that point. This does Markovnikov hydration. But it allows me to put in either a T or a D at the less hindered site, okay? At the site that has fewer carbons, or if you want more H's. The last point I make about this reaction is that it doesn't have to happen in water. It can happen in small alcohols: methanol, ethanol, propanol. Let's say, for example, it happened in let's call the alcohol ROH. What would have happened? Well, if you look at the mechanism, alcohols are also ionizing solvents, the small ones anyway. So it would still have ionized. The mercurial cation would attack the alkene to give the mercury bridge cation. But now, instead of water attacking, the alcohol would attack. And I would have ended up with this species. Okay? And then alcohol would come in, act as a base, pluck off the proton, and give rise to your corresponding ether. Okay? And if I'd used the borodeuteride, I would have brought in the OR and the D. So this is a wonderful reaction because it gives you lots of freedom. I can take the alkene, convert it to the Markovnikov alcohol, the Markovnikov ether. I can put in a D or an H at will. So there are lots of little degrees of freedom in the reaction, which are wonderful questions for synthetic evaluations. Okay, now both the acid catalyzed reaction and the oxymercuration reaction give me Markovnikov products. The latter, however, is superior because it never makes a carbocation. Because the flaw with the acid catalyzed reaction was, one, everything was in equilibrium, so the yields are bad, and two, the reaction makes a carbocation, which leads to potential rearrangements. All of these reactions go to completion. So the yields are really good. I mean, these are in excess of 90%. But more importantly, it never makes a carbocation. You end up with a carbon having a delta plus 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 charge, but never a carbocation. So the problems that attend the acid catalyzed reaction with the rearrangements don't occur here. And so this is by far the superior method for doing Markovnikov hydration. Okay. However, what if we wanted to make the anti-Markovnikov alcohol? Are we doomed forever to be unable to do that? The answer is no. We are organic chemists. We can do anything. So if I want to do anti-Markovnikov, I'm going to use hydroboration, oxidation. And this does anti-Markovnikov. So let's start again. Let's take the alkene. There's any number of agents I can use for this reaction. Most people use B286, which is fine. B286 works. I've done this reaction several times. There's a species called 9-BBN, which I'll show you in a second, which to me works a lot better. But in many texts, so in many of the exams that you'll see, they use B286, which is fine. And then we use hydrogen peroxide. And what that will give you is the anti-Markovnikov alcohol. Let's talk about this a little bit. B2H6 is functionally a dimer of BH3. Right? It's a bit more complicated than that, but let's, for this discussion, leave it that simple. So it's a dimer of B2H or BH3. BH3 is an electrophile, and a very good one. The boron does not have an octet. So the boron spends its entire chemical life looking for 2 electrons. This is a very potent electrophile. And as a consequence, it's a very toxic compound, because again, we are built of nucleophiles. So the guy who first was working on boron chemistry, I think it was Pauling, noticed several years into it that he was getting really sick. And he figured out it was because of the boron poisoning. And very cleverly, what he started to do is to document both the illness while he worked on the chemistry. So he did both chemical studies and medicinal studies on the toxicity of boron. A lot of which people actually use to develop a better understanding of the phenomenon. Okay, so this is an electrophile. This is an electrophile. Alkenes are nucleophiles. So obviously, both the boron and the alkene are going to undergo chemistry. So the way this reaction goes is that, and I'm going to draw the alkene, but this has a stereochemical consequence. I'm going to draw the alkene, right, as a planar species. The boron is also planar, because it's sp2 hybridized. And the boron reacts with the alkene in such a fashion, so the alkene is flat, the boron is flat. So the flat boron sits under, or over, doesn't matter, the alkene, right? But if you notice how it's configured, the boron sticks the H in towards the bulkier side. So the bulk of the borane hides away from the bulkier side of the alkene. Basic steric hindrance, trying to avoid steric hindrance. What happens next is the alkene attacks the borane, and you end up making this species. It's the one that was writing. This is called an organoborane. Right? So the alkene reacts with a boron species and gives rise to an organoborane. So what have I done? I added hydrogen and boron across the double bond. That's why this first bond is called hydroboration. In the last step, I'm going to simply oxidize the boron off the molecule using hydrogen peroxide. So hydrogen peroxide is a strong oxidizing agent. It will oxidize the boron off, and you end up making the corresponding alcohol, which, as you notice, is the anti-Markovnikov alcohol. All right, so that last step, so this sequence is the hydroboration. This part is the oxidation. I'm going to make 2 points. Point 1. The mating between the alkene and the borane makes perfect sense. Nucleophiles, electrophiles. There's a stereochemistry involved because you want a flat alkene react with a flat borane. Organoboranes are interesting compounds. I can oxidize off the group to make with hydrogen peroxide to make the corresponding alcohol. It turns out if I treat them with acetic acid, CH3COO, let's say D, I'll replace the boron by a D. So what I would get would be this compound. Now, just want you to make sense of this. What this means is I can actually